Well, hello, Math 251 students. I just wanted to give you a little video to watch over the spring break because I think this will be helpful to you in kind of staying ahead of the game with the material and maybe getting a head start on the problems that I've put up for you to work on for the homework. Gives me a chance to do a little bit of math during the break too, which I never object to. So I'm just going to do a couple more examples on this optimization topic, if that's all right. Essentially, we were talking about it in class on the Thursday before the break. If we have a function of two variables, we're looking for what we call the critical points. And those are the points A, B, where both partial derivatives f sub x and f sub y are equal to 0. And I should also add or undefined. Okay, so wherever the partial derivatives are either 0 or undefined, we have a critical point. Okay? Once we find our list of critical points, then we have this d test, or in other words, the second derivative test, where we calculate this expression d. d is fxx times fyy minus fxy squared. And we plug in our critical points into that expression for d. And here are some outcomes of that test that we talked about before. If d is greater than 0 and fxx is greater than 0, well then the point AB is a local minimum. All right? If instead the fxx is less than 0, well in that case AB is a local maximum. Finally, if d is less than 0, then regardless of any other facts about the partial derivatives, if d is less than 0, we have a saddle point. Okay? And if d is equal to 0, then the test really doesn't give us any information, and we have to think about another way to decide whether AB is a maximum or a minimum or a saddle point. I've got a couple of examples like that in the homework for you to look at, and we'll talk about them in class soon. So just be thinking about that a little bit. Now, towards the end of class, I had told you guys that sometimes you don't need to use this d test, right? If you're talking about a physical problem where there has to be a minimum or there has to be a maximum, then you sometimes, just from the nature of the problem, will know that you're talking about one or the other of those. So let me give you an example. I gave you an example of that in class. I gave you the equation of a plane, x plus 2y plus 3z equals 4. And I said, what is the point on that plane that is closest to the origin? Right? So that was an example of it. We did that one in class. Let me give you another example. And again, these are real world, like physical problems, actual physical problems in the real world. So this would be an example. A closed rectangular box, okay? A closed rectangular box of length x, width y, and height z. So suppose you have a box, its length, width, and height are x, y, and z, has a volume of 125 cubic feet. Okay, so suppose you have a particular volume to this box. Find the dimensions that minimize the surface area. In other words, they want you to find the x, y, and z values that will minimize the surface area of the box. Okay? So, here's a picture of what we're looking at, right? We have a box, something like this, right? Not the greatest artist here, but that's the idea, okay? So we have, the length is x, the width is y, and the height is z, right? Now, for the surface area of a box, notice that we have 6 sides to that box, right? The top and the bottom, the way I've set it up, the top and the bottom both have an area of x times y. Those are just rectangles on the bottom of the box. And then the front and back faces are going to have dimensions x by z. There's 2 of those. And then the sides, the left side and the right side, well, there's two of those, and they have area YZ. So this is our surface area equation. Maybe I'll just call it A. So the A is the surface area. Now, one of the problems with this formula is that it has three variables in it, X, Y, and Z. Remember that we really are mostly studying functions of two variables in this section. So the question comes about, how do you get rid of one of those variables? Well, that's where we have to take advantage of the volume. Okay, the volume was given to us. Of course, the volume of a box is just the length times the width times the height. And we were given that volume as 125. Okay? If I now solve that for Z, I will get 125 divided by X times Y. And this is how I can now go about replacing the Z, eliminating the Z essentially from the problem. So I'm going to go back to the area equation again, and I'm going to replace Z with 125 over xy. So we have 2xy plus 2xz. Okay, so 2xz, but z is going to be replaced by 125 over xy. And then I'm going to do the same thing with the 2yz. I'm going to replace the z with 125 over xy. So this can be simplified. Let me just simplify it for you really quickly. All right. I have 2xy. 2 times 125 is 250. And the x's cancel, leaving me with a y on the bottom. And then in the second term, same kind of thing, 250, this time x on the bottom. All right? So this is my area equation, and the next thing I need to do is try to find my critical points. I want to find the minimum surface area. So now that I have a function of only two variables, I can work on finding my critical points. So for example, a sub x, the partial derivative of this area function with respect to x, let's see. 2xy, the derivative with respect to x is just 2y. The middle term will become 0 when I differentiate with respect to x. The last term will be minus 250 over x squared. Okay, and we're going to set that one to 0. We're going to set that one to 0. Okay, I'll come back to that in a minute. Let me find my other partial derivative though first, a sub y. That's going to be 2x minus 250 over y squared. And again, I'm going to be setting that equal to 0. All right, with that in mind, I now can come back and solve these equations. Okay? I had mentioned in class that it's a good idea to keep the 0 on the right-hand side. That's, of course, not a bad thing to do. However, what I will say is that you really are leaving the 0 here so that you can factor on the other side of the equation. And here, there really isn't any factoring that you can do anyhow. So what I'm going to do instead, I'm actually going to just, well, the 2 and the 250 can be simplified. I'm simply going to do the following. I'm going to let y equal 125 over x squared. So if I take this equation and I move the 250 over x squared to the other side and then cancel a factor of 2, this is what I'll be left with. Y equals 125 over x squared. And I can do the same thing with the second equation, and I'm going to get x is equal to 125 over y squared. All right? I'm not the biggest fan of fractions, so I'm going to cross multiply those equations. X squared y equals 125, and xy squared equals 125. Okay? So far, so good. Well, actually, this means that these two equations are equal to each other, right? So we can actually conclude here now that x squared y is equal to xy squared. Normally, when you're canceling, you have to make sure you're not canceling a 0 from an equation. But in this case, notice that the x, the y, and the z have to be positive numbers. We are making a box here, so these quantities x, y, and z are not going to be 0. So I can cancel some x's and y's, and if I cancel 1x and 1y from each side of this equation, I will get that x is equal to y. If I put that information back into either one of the first two equations, I can see, for example, if I come back up here, that x cubed will equal 125. And that means that x is equal to 5, and since y is equal to x, y will also be equal to 5. Guys, we have found one critical point. There's only one critical point here. It has to be the one we're looking for. We don't need to test this 0.55 in the second derivative test because this has to minimize our surface area, right? It's not going to maximize our surface area. For one thing, the question is asking us to minimize the surface area. And furthermore, there really is no maximum surface area that I could make. I could make a box that was 0.00001 feet high, right, that took up a massive area in terms of the length and the width of that box. So you could make the surface area as big as you wanted if you were, making this box really, really short. There is no maximum surface area here. There's only a minimum. Okay, so I know that that has to be my solutions for x and y. Of course, then I can come back, and I just erased it. The z coordinate was 125 over xy. So if you put those values in for z as well, or for x and y you solve, but for z you get 5 as well. So the dimensions that you're looking for here, again, without ever using the d-test at all, is just 5 by 5 by 5. Length, width, and height are all equal to 5. In other words, it's actually a cube. It's the shape of a cube. Okay? I hope that makes sense. This is another example of a physical problem where the one critical point that you get has to be what you were looking for. Okay? Let me give you one more example. Okay? And again, you can pause this and rewind it. Watch it as much as you need to. That's the nice thing about a video. Let me give you one more example here. Find 3 positive numbers. This is similar to a homework problem, so I thought it might be useful to show it to you. Find 3 positive numbers whose sum is 100, so they add up to 100, and whose product is as small as possible. Okay, so let's try this. So in other words, when I add up the 3 numbers, I have to get 100. But when I multiply the 3 numbers together, I want that product to be as small as possible. So maybe I can call my variables x, y, and z again. Right? So x plus y plus z is equal to 100. And our product expression, let me call it p of x, y, z. Of course, this just means that we're looking at x times y times z. It's a little different than the last example, because on the last example, I knew what the product was. The length times the width times the height was 125, and it was the surface area that I was trying to minimize. So here, I'm trying to actually minimize the product, x times y times z, given that x plus y plus z is equal to 100. But, the strategy is going to be very similar. We're going to eliminate one of our variables. I'm going to eliminate z by solving for it, and then I'll put it into my product equation in terms of just x and y only. So now I have x times y times whatever z was. Well, that was 100 minus x minus y. So this becomes 100xy minus x squared y minus xy squared. Okay. I start working on my partial derivatives again. We're going to look for the critical points of this function of 2 variables. When I differentiate with respect to x, I get 100y minus 2xy minus y squared. Okay. And when I differentiate this with respect to y, I'm going to get 100x minus x squared minus 2xy. And both of these need to be equal to 0. Now all three of those numbers, x, y, and z, they are all positive. They are all positive. So none of them can be 0. None of them can be 0. So for example, the first equation there, you see that you can factor a y out of it? You can factor a y out of that and leave yourself with something that looks like this. And the second equation, similarly, I can factor an x out of the second equation. And if I do that, I'm going to get this expression. I'm trying to solve these equations right now for x and y. But because x and y are positive numbers, then I know I can cancel them. They're not going to be 0. So I just leave myself with these other two equations. So 100, let me move the 2x and the y to the other side, and I'll do the same thing on the second equation. I'll move the x and the 2y to the other side. So 2x plus y is 100, and x plus 2y is 100. All right? So if I actually take these two equations, I basically want to solve them. Two equations and two unknowns. Two equations and two unknowns. One way to do that is to just set them equal to each other. If I just set them equal to each other, I'll have the opportunity to cancel on both sides of the equation, and look at that. Once again, I get x is equal to y. If I go back and plug in that information into either one of the two equations, if I replace the y with x, I'm just going to get 3x equals 100. So x is 100 over 3, y is 100 over 3, and if you now go back and substitute what z would be equal to, you're also going to get 100 over 3. So this is, again, this is the only critical point that we found, so it must be the point that we're looking for. Okay, I hope that these physical examples have made sense. You're going to find problems on this in section 13.9 in the book. Give it a shot. If you have questions, you can email me over the break, and we're certainly going to talk about the homework when I come back, and when we come back the first week of April. Okay, thanks guys. Thanks for watching. Take care.